Okay, today we're going to talk about standing waves. And standing waves are produced by interference. And so you can kind of think of this like a jump rope where you are twisting one end and you've got someone twisting another end, and you're going to make basically a loop. Well, if you were to hold one side stationary, like against a wall, and you move it at just the right frequency, you can actually get a standing wave where the interference, the crests and the troughs happen at the same time. And so you have your nodes, which are the fixed ends here, and then you have antinodes, which are like the loops. And so we can see standing waves. Now they have to be, the interference has to be at just the right frequency to produce that. If it's off at all, then you're going to end up with just a bunch of different waves. You're not going to end up with this nice, beautiful standing wave like that. So we have a few equations. First off, we're going to talk about standing waves. These are just on a string, and then we'll talk about sound waves and how they work with tubes. Standing waves on a string also work with all your string instruments, but the sound waves are a little bit different when we're talking about on a tube. Just some terminology, the lowest frequency is going to be called the fundamental frequency. The fundamental frequency has only one anode, and this is to half wavelength is what this is. This is the second frequency because this is one anode and then two anodes. So this would be your second frequency, or your second harmonic is how we refer to it. So to calculate the fundamental wavelength on a string, so this is when you have just the one node. I'm going to draw it over here. So we have, here's our wave, and it looks like that. So we have just the one node. Okay, to calculate that one, you have your wavelength, and this is half of a wavelength. So the wavelength is 2 times the length of the string. So L is length of string in meters, and then lambda is wavelength in meters also. Now to figure out the frequency that you have to have in order to produce that standing wave, the formula is a little bit more complex, but it really boils down that this is your wavelength, this is how many nodes that you have, and this is your velocity. So really, we're just modifying that velocity formula for here. This formula is not on your notes because it's just a modification of this one here. Okay, so your wavelength was 2L. So if we're solving for frequency, it's velocity divided by wavelength, and that's here. And so if we have like 2 nodes, this would be half, or the full length is 1 wavelength. And so we can account for that with that N value. Okay, so F is going to be frequency, seconds to the -1, or remember hertz. We'll write both of those down. N is going to be the number of antinodes. And in this case we're going to be talking about the loops. This is what N stands for is going to vary depending on whether we're talking about a string or a tube. So here it's the number of antinodes, and there's no unit for that. V is the velocity in meters per second, and then L is again the length of the string, measured in meters. Okay, so the difference between a standing wave and a traveling wave is that a standing wave is going to have the nodes at the end. Okay, and nodes is again where it comes together, and then it's going to reflect back. And you're going to have that nice, beautiful little pattern that would create like a jump rope. A traveling wave is just going to travel through the medium. There's not going to be any reflection whenever we have a traveling wave. So rather than if it was a traveling wave, it would hit the wall or it would continue on. There would be no reflection on that. Okay, so on the diagram below, we want to label the nodes and antinodes, and then state the amplitude and wavelength of the standing wave and the harmonic number. So we're going to use 4 different colors here so that we can label all of our stuff. The first thing that we're going to label is going to be our nodes. And I'm going to label them with this pink color. Okay, and the nodes are going to happen whenever you have this destructive interference, so it cancels out, and these points at the middle. The antinodes, I'm going to label in orange. Okay, so that's going to be these up here at the top. Or the bottom. Okay, this is where the constructive interference happens, because that's going to have the largest amplitudes. Now, for this one, we're going to just do the amplitude of the largest one. Okay, so that's going to be this distance here, from the center up to the top. And then we'll do the wavelength. And that's going to be, so here we have our one wave here, and then it starts repeating itself. So here is our wavelength. Now we can identify which harmonic this is by counting the number of antinodes. Okay, so here we have 1 here, 2, 3, 4, 5, 6, 7. So that makes this the 7th harmonic. Okay, so we have 7 antinodes. Or 7 loops, if you want to count them that way. Okay, the frequencies of each harmonic will relate to the fundamental frequency because they are multiples. Of the fundamental frequency. Okay, so they are multiples of the fundamental frequency. That's as far as we're going to get today. So on the next one, we're going to talk about sound and how that relates to strings and air columns. Like we're going into instruments, so string instruments and wind instruments, essentially. So see you next time.